Hello everyone, it's Mr. Pope from Wilmington Grammar School for Boys. Today I'm going to be looking at competitive maths, recreational maths. Usually on Sundays I'm going to do something a bit fun or just a bit different that's not on specification, whether it's GCSE or A level. And generally looking at things that stretch the mind, make it more flexible, hopefully make it quicker. I know those are vague descriptions of mental abilities, but essentially what universities, if they do give you an interview for, if you want to go for, or just generally in life really, I don't think problem solving skills can ever be overrated. So today we're going to be looking at the pink kangaroo. So what is the pink kangaroo and what's the UKMT? Well, as far as I'm aware, the UKMT is the United Kingdom Mathematics Trust. You can Google it. There's plenty of information out there. I'm pretty sure if you just Google UKMT, their website will come up. They're a great organisation. I forget which university it's based from. I want to say Leeds. Could be Leicester. L is sticking in my mind for some reason. I think it's Leeds. And now they run various competitions for school kids up and down United Kingdom, mainly for secondary, I think, although I do think they have outreach programs. To be honest, I'm not entirely sure, but you can Google it and you can find out. And in actual fact, it's probably better if you do. But you've probably heard of it before. And they have national competitions where, depending how you get on, the junior challenge, intermediate challenge, and the senior challenge, individual challenges, they're all secondary school based mathematics competitions, multiple choice. I think they're about an hour each, and it depends how you get on with them. And should you do particularly well, then there's various other follow-on competitions you can apply for, that you qualify for. One of them is the pink kangaroo, and I want to say off the top of my head, it's for year 10 and year 11 students only. So I think there's different, I think it's the McLaurin, Hamilton and Cayley papers for the seniors, and I think it's the grey kangaroo for year 9s. It's all on Google, but they're brilliant competitions to do, and if you ever qualify for one, that's something great to put on your personal statement. So they're designed, these papers, not just any particular maths, but at the same time they're supposed to be accessible. What does that mean? It means it doesn't matter what your school has taught you in terms of your subject knowledge. It's more your problem solving, general number and algebra. However, having said that, you can bet that I'm pretty sure number theory, quadratics, some circle theorems, geometry facts will help massively. But essentially, there's two main tips. Well, there's many main tips, and I'll go through them in separate videos. But there's two tips that I want to work through today. One of them's a small point, and that small point is that UKMT and a lot of maths challenges, not just UKMT, various other ones, especially if it's a yearly competition, they like to have maths questions that are themed to the year. So what do I mean by that? Well, the year is 2015, in this case, the one that I'm going through today. I'll go through other years at other points. I might skip out a few. I might set some as a worksheet for you to work through. And they're so great. I mean, you don't have to do them in time conditions. I mean, what I'd probably do is I'd do an hour in time conditions, and then I'd, in a different colour pen maybe, attempt the rest at my own time, or go back and then just honestly mark how I'd get on. But anyway, the year is 2015, so I might be interested in knowing different facts about the number 2015. Well, what are its prime factors? That's a key one. So 5 goes into it. That's fairly key. 15 is 3 5s. So it's going to end in 3. And 20 is 4 5, so 200 is 45, so 2000 is 403 fives. And then divisibility checks are always a good one as well. So do you know your 2, well, they're even numbers. Do you know 3? Well, that is when the digit sum is a multiple of 3. If it's divisible by 5, it ends in a 0 or 5. And then after that, people get a little bit confused, and it's a bit, well, it gets a bit dicey at that point. So I'm going to show you some divisibility tricks, and in actual fact, I'm going to show you a way of making your own divisibility tricks. So the first thing you want to check, right, is if you want to find the factors of the number, it's always a good idea to approximate the square root. So, well, I know that 20 times 20 is 400, and 21 times 21, I believe, is 441. Well, it doesn't matter what it is. The point is the square root of 403 is going to be 20 point something. So that means I only have to check all the prime numbers up to and including 20. So 2, 3, 5, 7. Next one's 11, 13, 17, 19. So we might as well check all the divisibility proofs here. So for 11, I'll skip 7 because 11's a special case, but all the other ones after that, it's fairly nice. The 11's is the alternating sum has to be divisible by 11. So I don't know, let's pick a number. 1331 is 1331 divided by 11. Well, if I write that number again, but now I put plus, minus, if this number is divisible by 11 and it's 0, and clearly 0 can be divided by 11 with no remainder, then that means 1331 is divisible by 11. I mean, these checks are good because they're quick, and it kind of tells you whether it's even worth doing long or short division or chunking, whatever you kids are being taught now at school. So alternating sum is divisible by 11 for 11. For 7, it's you take the last digit, double it, and you subtract from the truncation. Okay, so what does that mean? Let's take a nice example. Let's take 14. I take the 4 away and double it, so it becomes 8, and then I subtract it. 1 minus 8 is minus 7. Minus 7 is divisible by 7 because it's minus 1 times 7, so that means 14 was. So if I pick a crazier example, let's say 1, 2, 3, 5, 7. Then if I take the 7 off and double it, that's a 14. If I subtract it, 5 minus 4 is 1, 3 minus 1 is 2, 2, 1. I don't know if 1, 2, 2, 1 is divisible by 7, so I play this game again. 1 doubled is 2, take it away, so that's 120. I mean, you can probably tell that 120 is divisible by 7, but let's play this game again. Take the 0 off, double it, take it away, that's 12. 12 is definitely not a multiple of 7, so that means 1, 2, 3, 5, 7 is not a multiple of 7. Yeah, just a really quick way. Now you can play this game with 13, 17 and 19, and pretty much for all primes onwards, it's all about taking the last digit, multiplying it by something, and then adding or subtracting from the truncation. And you can actually guess with a lot of these. So, I don't know, let's say 13. Well, if I take the 3 away, can I make what's the easiest way of making a 13 again? Well, if I times it by 4 and add it on, so 3 times 4 is 12, 12 add 1 is 13, that works. Let's try a different one with 13. Let's try 39. So if I take the 9 off and I times it by 4, that's 36, add it on, that's 39. That also works. Let's try a more exotic 13, so let's say 13 times 27. 7 times 3 is 21. 7 times 1 is 7, plus the 2 is 9. 6, 2, so it's 1, 5, 351. So 3, 5, 1. Take the 1, quadruple it, so it becomes a 4. add it on, that's 39. Is 39? Yep, we've done that already. So yes, it is. With 17, well, let's think about that. If you take the last digit off, a multiple of 17 is 34. So what I can do is I can times the last digit by 5 and then take it away, because 7 times 5 is 35, 1 minus 35 is minus 34, and that will work. So let's try a different one. Let's try 17 times 23. 3 times 7 is 21, 3 times 1 is 3, plus the 2 is 5, 2 times 7 is 14, 2 times 1 is 2, 192, so 291, will that work? 291. Okay, what do we do? Last digit times 5, bosh, and then, what did I say? Subtract. Doesn't seem to, have I done this right? Mm-hmm. 3 times 7 is 21, yeah. Oh lol, that's where I made a mistake, you silly boy. That's 340, so it'll actually be 491. God, I'm making mistakes everywhere now, is that right? 0.5 plus, no, 391. God, silly. Okay, so this should have actually been 391. 39 minus 5 is 34, so yeah, that checks out. And so on. Now, to actually prove why this works, well, we're going to have to do a lot more number theory to prove that. But essentially, there's a whole list of divisibility proofs. In actual fact, again, Google them, you know. I think if you know your divisibility rules up to about 41, 43, then you're doing incredibly well. And they save time, you know, they really do save time. You know, if a good student has memorized the divisibility rules up to 41, 43, then essentially they can find the prime factors fairly easy of numbers of the order of 41 squared, which is above 1600. And 43 squared, well, what's 43 times 43? 3 times 3 is 9, 3 4s 12, and then 4 3s are 12, 4 4s are 16, plus that's 17, so 9, 4, 7 plus 1 is 8. They know numbers up to 1849, but then if you think about it, 44 isn't prime, 45 isn't prime either, 46 isn't prime, 47 is. So really they can approximate numbers up to 46 squared, and 46 times 46, 6 6 are 36, 6 4s are 24, plus 3 is 27, 4 6s are 24, 4 4s are 16, plus the 2 is 18, 6 7 is 1, 1, 1. So really, if you know the prime divisibility is up to 43 squared, then you can calculate all the prime divisors up to 2116 fairly quickly. Now, why is that good? Because, well, the year is 2020, so this is in like 94 years' time. You know, so this technique, or these techniques, will easily set you up for your lifetime, my lifetime, your kids' lifetimes, that kind of thing. So prime divisibilities of facts and knowing things about the year is also quite interesting as well. And the second point, which I'm probably going to labour just as much, is counting strategies. Oh dear, this visualization, counting things, oh dear, that's terrible. Counting strategies come up all the time. And the reason why they're so important for me in terms of, now when I say important, I mean in the context of competitive maths like the UKMT. The reason why they're so important is because this qualification, this exam, this assessment is only 1 hour long. And you have got to make your counting efficient, correct, and easily checkable. Now, if you don't have a counting strategy, then your only option, if no strategy whatsoever, then your only option is brute force, and you make an exhaustive list. That is your only option if you don't have some form of counting strategy. Right, why is that bad? Well, let's suppose you have, I don't know, a bike lock with 4 digits, and those digits can be from 0 to 9, and there's some condition on those things, and you have no idea of how to pinpoint those things down. So what do? Well, you've got four lots of 10 for things for combinations. You've got a times 10 in the first slot, you've got times 10 in the next slot, times 10 in the next slot, times 10 in the next slot. It doesn't take a genius to work out that you've actually got 10,000 combinations to cycle through. Let's get that into context. 3,600 seconds is in 1 hour, because it's 60 seconds in a minute times 60 minutes in an hour. We're looking at even if you were to list out, check and compute each combination in 1 second, you would run nearly 3 times over the time you've gotten. And this is just for something silly like 4 digits from 0 to 9. A lot of the time, this won't come up, probably not, because it's not silly, but the point I'm trying to make is that listing out by brute force lists for humans is a long, laborious task, and it wastes so much time. One of the great things about computers is they can list out things so much quicker than we ever will be able to. And that's one of the main reasons why we rely on computers so much, is because they can store lots of things and they can compute very simple things incredibly quickly. And one of them will be just to be checking lists, ordering lists, that kind of thing. And we talk about that more in decision maths, which is what I talk about on Saturdays, I believe. Or Fridays, I can't remember. Check on the schedule. So, counting strategies, okay, we need them 100% because it will save us time, I promise. Another bit of anecdotal evidence is there's also team competitions going on, and I remember one year, might have been 2016, 2017, I can't remember, but when you go to these team competitions, for UKMT anyway, you'll take a team, a teacher will go with you, and sometimes, well, every time that I've been, the teacher then gets rotated round and the teachers swap, so they have to invigilate the scores of other teams. And what happens is that, you know, the teacher marks your work as and when you get on, that kind of thing. And it's quite nice because in the breaks you can talk to the kids from other school, how they're getting on, are they enjoying maths? Well, they clearly are, but it's always nice to ask them, that kind of thing. So what's the point I'm getting at? I remember there was one team, and there's 3 rounds. There's the group round where they can answer questions in any order, and that's fine. And they can do it how they want to. And during that time, teachers are usually sent off to a separate room and trained in the upcoming events and how to mark them properly. And then the second round is usually a cross number, where it's like a crossword, but the clues and the entries are all digits from 0 to 9. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And this team had scored 100% in the group round, and they were pretty much nearly done with the cross number. I think they only had like 2 or 3 entries, and those 2 or 3 entries they really did greatly depend on this one. I can't remember if it was a down or a cross or whatever it was, but the question had something to do with combinations of something, and these guys had, I think there's usually about 60 spaces to fill out. They might be above or below like 57, 58 or 62 because they've got to make a crossword, and it's not easy to make an exactly 60 point round for a cross number. But anyway, so these guys, I say guys, like these students, they pretty much banged out the entire cross number in like 10 minutes. They were so good, so blisteringly good. And then this one question came up where I didn't think it was particularly difficult, but it was about combinations and ordering things, and it was something like I can't remember. It was something silly like the word aardvark can be listed out if you rearrange the letters. How many ways can aardvark be rearranged? And they just brute forced it. They just listed out every single combination alphabetically, and it took them good 15-20 minutes. Now, bearing in mind the round is 40 minutes long, you know, they wasted so much time. They could have done the whole thing if they'd just known a counting strategy. They could have done the whole thing in seconds. And there's actually, you know, I felt the generous thing to show them it afterwards, and they're like, oh yeah, and then I gave them an example, another one, and they literally banged it out in like 20 seconds. They were so good. But, you know, don't feel bad. I mean, it's not uncommon for students to be so good at everything they've been taught, and then this little weakness comes in and it just falls apart. And, you know, just because you're good at GCSE maths or A-level maths, there's so much more maths than just that. And I think like there's some things people have a natural grasp for. They just kind of order things or structure things in a certain way, or they've just got the mental flexibility to try something new. And so you should never feel intimidated if someone's in your class is getting like 100% all the time. And, you know, conversely, if you're getting 100% all the time, you shouldn't be feeling that, you know everything. And there's so much more. Anyway, counting strategies. I don't think they're mentioned enough in GCSE or A-level. Maybe that's why UKMT pestered them so much. So, okay, I'm going to go through a really simple example, and then I'm going to go through a more complicated one. So let's start with a really easy one. Let's say I've got 3 boxes, 1, 2, 3. Okay, and now I want to make this distinction between something called combinations and permutations. Okay, the more experienced mathematicians will probably see where I'm going with this, but combinations, I'm going to define them as where I pick numbers and I don't care about the order. And permutations is where I would pick them, but order matters. Okay, now it's really clear to make that distinction. So let's say, for example, the question is, I've got 3 numbers here, and I want to choose any 2. And I don't care about the order. Well, that's a combination. So how many combinations are there for this? I've got 3 numbers and I want to choose 2. Well, I can either have 1, 2, or 1 and 3, or I could have 2 and 3. Okay, there's only 3 combinations of picking 2 numbers. I can either have 1 and 2, 1 and 3, or 2 and 3. Now I've picked this example because there's only 3 numbers, and it's quite easy to see why that's the case. But suppose I had a big list of these numbers and it went up to say 25, then immediately it becomes more complicated. But if we've got this system down, actually it's just a calculation. We can do it fairly quickly. Now if I look at permutation where the order does matter, then well, we still got 1, 2, 1, 3 and 2, 3. But now 1, 2, there's also 2 and 1. We could have picked the 2 first and the 1. With 1, 3, we could have picked the 3 and then the 1. And then with the 2 and 3, we could have picked the 3 first and then the 2. Okay, so I'm going to give you a couple of formulas, and to be honest, I've chatted for about 25 minutes already, and I wanted to do an hour competitive maths video on the UKMT 2015 paper. So if you want to see proofs of this, please look at you know what? I'm just giving it away. This is Combinatorics. You know, if you want something fun to look up, Combinatorics, absolutely brilliant, because there's so many problems that you can solve really easy that if you ask people, like they'll just be like, what? They can see it in their head that you're asking them to sort out so many things, but actually you can telescope these things fairly quickly. So I'll give you the formulas for combinations and permutations, and I'm going to give it the classical way. But before I do that, there's one thing I have to define, and this idea of a factorial, this question mark thing. And there's various ways of defining factorial. One of them is as a recursive way, which is n minus 1, no, it's n plus 1 factorial over n plus 1. Or another way of defining it, I mean, there's loads of ways. I could introduce the gamma function, but that's definitely way beyond what we've currently done so far. We will get onto it, I'm sure, in the calculus section. But for now, just computing things. When n belongs to the set of integers, let's have the integers, but let's have the positive integers, and n, well, n could also be equal to 0, and we'll talk about that in a second. But essentially, what is n factorial? It's where you take n and you multiply it by the next number down, and you multiply it by the next number down after that, and so on until you get 3 times 2 times 1, and it ends. So an example, 2 factorial would just be 2 times 1. 1 factorial would just be 1. 3 factorial would be 3 times 2 times 1. 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1. Okay. Now 0 factorial, you're probably thinking, what? How can you do it that way? It starts at 0. Well, then look back to the previous example in the recursive form. It's the next factorial on, so that's 1 factorial over n plus 1. Well, if n is 0, 0 plus 1 is 1. And 1 factorial over 1 is just 1. Okay, now the combinations and permutations. Right, so with combinations, we use the big C and we say n choose R. And in our case over here, we did 3 objects choose 2. And the way it works is it's n factorial over r factorial times by n minus r factorial. So what would the calculation have been there? It would have been 3 factorial over r factorial, which is 2 factorial times n minus r. 3 minus 2 is 1 factorial. So 3 factorial is 3 times 2 times 1 over 2 factorial, which is 2 times 1, times by 1 factorial, which is times by 1. The 2 and the 1 cancel with that 2 and the 1. 3 over 1, the answer is 3. Easy peasy, lemon squeezy. So this is the combinations. That's the formula for it. We actually look at this a little bit. Not really. I mean, we kind of do, but we're not really. Not in the context of choosing problems. We use it more for the binomial expansion in year 12. But to be honest, we don't use it as much as... Anyway, so for permutations, this is also quite easy. So n permute r, this will just be n factorial over n minus r factorial. Okay, so let's see how our calculation would have looked like if we had 3 objects and we wanted to find the different orders of choosing 2. So this would have been 3 perm 2, which would have been 3 factorial over 3 minus 2, which is 1 factorial. So 3 factorial is 3 times 2 times 1. 1 factorial is just 1. The top is 6, the bottom is 1, the answer is 6. And that does agree with what we found heuristically. Okay, now More complicated examples. Let's go back to the maths challenge. So, what was it? Aardvark? I never. Oh, how do you spell aardvark? Is it Aardvark? Just going to quickly Google this. Aardvark. Pretty sure that's how it's spelled. To be honest, that might have not have been the. Yeah, A-double-A-R-D. Yeah, got it right. Okay, so how many different ways can you rearrange the word aardvark? So these kids, I think they started with A, D, K, R, V, and they kept on going down and down and down until they're left with V, R, K, D, A. And it was just a horrible mess. You know, it really was. I mean, it took them pages and pages. They divvied it out within their team, and they got there in the end. But, oh man, it was so painful. And this is what you need to do. What you need to look at, okay, is, first of all, you count how many repetitions there are. So there's 1, 2, 3 A's. So the way to look at it is there's 1, 2, 3, 4, 5, 6, 7 spaces. So 1, 2, 3, 4, 5, 6, 7. So if there's 7 objects, choose 3 of them for where the A's are going to go. So to deal with the A's, it's 7, choose 3. And then you've got to multiply by, well, the different letters. And there's no other repeats here. So D, there's only 1 D. But there's 3 spaces gone, so there's only 4 spaces left, choose 1. And then there's 3 spaces left, and we're going to sort out the K, and there's 1 K. Times by, there's 2 spaces left, and we'll choose for the 1 R. And then there's 1 space left, and we'll choose for the V. So let's deal with some really simple ones then. First of all, 1 choose 1 is just 1. Why? Because I've got one object. How many ways are there of choosing one thing? It's just 1. 2 choose 1. How many ways are there of choosing one object from 2? That's also easy. That's 2. Similar logic. 3 choose 1. How many ways are there of choosing one object from 3 things? There's 3. You could pick any one of the 3. 4 choose 1. Well, how many ways are there of picking one object, one thing from 4 objects? Well, there's 4. And so 4 times 3 times 2, well, that's quite easy. This whole thing here is going to evaluate to 24. So it's just 24 times 7 choose 3. And the trick to this is things might cancel, so I'd leave it as 4 times 3 times 2 times 1. And now 7 choose 3. Well, let's go back to our thing. It's going to be 7 factorial over 4 factorial times 3 factorial. And why have I left it like that? Because 4 factorial, that cancels with this. So all we have to do now is work out 7 factorial over 3 factorial. Well, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. And 3 factorial is 3 times 2 times 1. And now look, the 3, 2, 1 there cancels with that. So we're left with just a really nice simple calculation as 7 times 6 times 5 times 4. And 5 times 4 is 20. And 7 times 6 is 42. 2 42s are 84. So the answer is 840. Now 840 doesn't seem a lot, but if it's going to take you 3 or 4 seconds to think about what the next combination is going to be, and so on, and then a couple of minutes to check at the end to make sure you haven't missed one, I mean, you've spent a lot of time rearranging this stuff around, and to be honest, you just don't have it. Now let's take a slightly more difficult example. And this is my personal favourite: sausages. Okay, now on the surface of it, you're probably thinking like, oh, well, this is a really good one, because to me, there's lots of multiples going on here, and if you don't have a counting strategy, you're going to be here all day. And to be honest, you could play the same trick with Mississippi. Oh, that's a good one, Mississippi. Anyway, let's go through it. So sausages. Well, same deal. Let's count We've got 1A, 2 A's there. And we've got 1, 2, 3 S's, and the rest are singular. So how many letters are there? 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 choose. How many S's? There's 3. Times by, well, there was 8 and it's gone down 3, so there's 5 spaces left. We'll do the A's, so that's 2. And then the rest are singular, I believe. So there's 3 spaces left, choose 1. 2 spaces left, choose 1. 1 space left, choose 1. As we've seen before, 3 choose 1, 2 choose 1, 1 choose 1. That's just going to cancel to 3 times 2 times 1, which is 3 factorial. 8 choose 3 is 8 factorial over 5 factorial, 3 factorial, times by 5 choose 2, which is 5 factorial over 3 factorial times 2 factorial, and then that's times by 3 factorial over here. Oh, look at this. The 5 factorials cancel, the 3 factorials cancel. That's amazing. So now we've got 8 factorial over 3 factorial times 2 factorial, which is so much easier to compute instead of listing stuff out. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, all over 3 factorial. Well, that gets rid of the 3 and the 2, and the 2 factorial is just 2, so I can cancel this 4 down to a 2. Okay, so let's do some stuff. 6 times 5 times 2 is 60. And then 8 times 7 is 56. All I have to do is 56 times 60. I've done that the wrong way around. Well, 6 times 56, 36. Is that 3,360? Yeah, there's no way. Okay, so for sausages, if you listed out every single combination alphabetically, and you did each word in 1 second, that would take 3,360 seconds. And we already know that 3,600 seconds is the hour. So, oh dear, you would have not a lot of time. In actual fact, you would have 240 seconds left, which is 6 minutes. Wow. So if you listed out sausages, 1 word every second, which by the way is blooming quick, especially, you just wouldn't do it. It's just, I mean, you could, theoretically, I just think it's highly unlikely to do. Whereas that took me a minute, 2 minutes, 3 minutes, not particularly long, so much time saved. And then Mississippi, I mean, if you want to pause this and give it a go yourself, fine. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. If I've spelt this right. I apologise if I haven't spelt it right. Oh God, let's Google it. Mississippi. M-I-S-S-I. Oh yeah, boom. There you go. Cool. So how many were there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There's 11. So it's going to be 11 choose. And then there's 1, 2, 3, 4 I's. There's 1, 2 S's, sorry. There's 1, 2, 3, 4 I's. There's 2 P's and 1 M. Okay, so let's do alphabetically the repeats. So I's come first, that'll be 11 choose 4. Times by, now if 4 have gone, 11 minus 4 is 7. So we've done the I's. Let's do the P's alphabetically, so that'd be 7 choose 2. Times by 5 choose, and there's 4 S's, so that, and then times by 1 choose 1. Okay, 1 choose 1 is just silly, that's just 1, so we don't have to worry about that. So the first thing is we've got 11 factorial over 11 minus 4 is 7 factorial over 4 factorial, times by 7 choose 2, which is 7 factorial over 7 minus 2 is 5, times by 2 factorial, times by 5 choose 4, which is 5 factorial over 5 minus 4, which is 1 factorial, 4 factorial. Let's look for cancellations. Well, the 7 and 7 go, that 5 and that 5 go, 1 factorial is just silly. So what we're left with is 11 factorial over 4 factorial times by another 4 factorial times 2 factorial. And this isn't actually so bad, because now, what's going on? Oh, that's my other question. So then that's going to be 11 times 7, oh geez, not 7. 11 times 10 times 9 times 8 times, and I won't write much more, I'll go up to the 4 factorial. And the reason why I've done that is you'll see in a second. Because on the bottom, I've got 4 factorial, 4 factorial, 4 times 3 times 2 times 1, and then another times 2 times 1. So that 4 factorial and that 4 factorial cancel. Well, I can get rid of the 2 and the 1 to make that a 3. I can get rid of that 3 to get rid of that 3. I can get rid of the 4 and 2 to get rid of that 8. So really what I've got is 11 times 10 times 9 times not 8 anymore times 7 times 5. Okay. So 9 times 10 is 90, times 11 is 990, and 7 times 5 is 35. So we've got 990 times 35. 5 times all that, 5 times 9 is 45, 5 times 9 is 45, so 0, 3 times 0 is 0, 3 times 9 is 27, 3 times 27 plus the 2 is 0, 5, 9 plus 6, 1, is that 13? Yeah, it is, and 13 plus 1, 14, wow, 34,650. So again, that's nearly 10 hours. So just rearranging Mississippi would have taken you 10 hours. And it would have brought confusion because the S's and I's, you'd be like, oh, have I covered that already? Yeah, it's not nice. Don't do this to yourself. I may have wasted like 20 minutes going through this, but I have probably saved you hours of just getting to the point of it, being able to compute things, and being able to systematically go, bam, I can arrange things exactly how I want them to be. So, sermon over. Counting strategies, so important, saves so much time, and it lets you race through questions so quickly. Okay, so now, the main part of the video. So, here it is. Pink Kangaroo. This was set on the 19th of March 2015. You're given 1 hour. You are given 1 hour. You're not allowed calculators or any kind of measuring instruments. Essentially, just go in there with a pencil. A HB or a B pencil, just a standard pencil. Don't go in there with anything flashy. I don't think you're allowed squared paper. I think if you ask for paper, you get plain paper. Don't bring in a ruler. Just bring in a pencil. It's all you need. Pencil and a rubber. Ideally, one of those pencils with a little rubbery thing on the end. That's it. And a pencil sharpener. That is literally it. You're golden. You really are. I like this. The question on the paper challenge you to think, not guess. You get more marks and more satisfaction by doing one question carefully than guessing lots. Yeah, that's fair. Does it tell you... usually you get marks deducted off. I don't want to peek. Oh, okay, that's the next page. 5 marks will be awarded. Oh, wow. Is there no penalise? Usually there's penalisation. It doesn't seem to be the case here. Maybe I'm wrong. Okay, so I'm going to set myself 1 hour. I haven't peeked at this yet. So, stopwatch. Yes, it's timer. 1 hour. Okay, 3, 2, 1, go. Okay. What is the units digit of the number 2015 squared plus 2015 to the 0 plus 2015 to the 1 plus 2000... Oh, okay, I see what they did there. They've got 2015, the digits of 2015, as powers of 2015. Haha, how clever. Well, this is quite easy because 2015 squared is just going to be a big number ending in 5. 2015 to the 0 is just going to be 1. 2015 to the 1 is just 2015. And 2015 to the 5 is going to be a massive number but ending in 5. 5 times 5s always end in 5s. That's just, I don't know, simple stuff. So if I was to add them all up in a column, I've got a 5, which is this is going to be a 10, so that will roll over to the 0. Add the 1, becomes a 1 in the digits column. Add a 5, it's going to be 6. Easy peasy, lemon squeezy. Okay, the diagram shows a square with sides length A. The shaded part of the square is bounded by a semicircle. Okay, what is the shaded area? Okay, so there's multiple ways of doing this. I think for me, the quick, intuitive way is if I cut this up. Oh, that's terrible. Oh, it's terrible. Oh dear, do it again. If I cut this up into 2 sections like this, and I take this and I rotate it, it should fit like that. You can probably see. And the reason why that works is because the radius of this semicircle, which is half the square, is the same as the radius of the white semicircle. So really the 2 white semicircles, or the white semicircles that are hidden by them, they're the same. So, you know, if you wanted to do some pi r squared and then minus bits, you can do, but you can probably notice that this area here can be wedged in this one here, and so on. So it looks like if the whole square is a by a, which is a squared, then the shaded bit is just a squared over 2. I mean, how much time you want to waste on that, it's up to you. You can just intuitively spot it. Okay, Mr. Hyde can't remember exactly where he's hidden the treasure. What a wally. He knows it at least 5 meters from the hedge. Okay, stop. 5 meters from the hedge. Well, this is including bits next to the hedge, so that's dumb. So C's definitely out. And it's at most 5 meters from the tree. So that means it must... Okay, so it's a loci question. So 5 meters from a tree is going to be a radius of 5 from a tree and shaded inside. But if that overlaps with the bit to the fence, there's going to be like a top bit. So it's clearly A. This is more than 5, so that's dumb. This is dumb, and this just isn't even the right shape. So the answer is A. Okay, 3 sisters bought a packet of biscuits for £1.50 and divided them equally amongst them, each receiving 10 biscuits. Okay, so there's a total of 30 biscuits. Hold that thought. However, Anya paid 80, Barini paid 50, and Carla paid 20. If the biscuits had divided in the same ratio as the amount they paid, how many more biscuits would Anna have received than she did originally? Okay, so the ratio is 8 to 5 to 2, and 8 plus 5 plus 2 is 15. Now, if I want to scale this up to 30 biscuits, I double it, so that's 16 to 10 to 4. So actually, Anya should have received 16, but she only got 10, so she should have received 6 more. Bosh. That's pretty easy. Each of the children in a class of 33 children either likes PE, computing, and 3 of them like... Oh, Venn diagrams. We've done this, man. We did this. Yeah, okay, man. Okay, so what is it? PE. Computing is over here. And 3 of them like both, so 3 go in the middle. The number who only like PE is half as many who only like computing. So we'll call this x over 2, and this is x. Okay. How many students like... so we want to work out what x plus 3 is, and we know that x over 2 plus x, which is 3x over 2, because it's 3 halves of x. So essentially x is 2x over 2, plus 3, this equals 33, the total amount of kiddies. So minus 3 is 30, so 3x over 2 is 30, so if I divide by 3, then x over 2 equals 10, so x is 20, so x plus 3 is 20 plus 3, which is 23, so the answer is 23, bosh, it's the last one. Easy peasy. There, Venn diagrams, man, they came up again. Okay, which of the following is neither a square or a cube? Indices, 2 to the 9, well that's 2 cubed, power rule, so that's out. 3 to the 10, well that's 3 to the 5 squared, so that's a square, so that's out. 4 to the 11, well that's 2 squared to the power of 11, or 2 to the 11 squared, because these are multiplying, and you know it's what's the word, not transitive, it's commutative. You can distribute that, 2 times 11 is the same as 11 times 2. So that's a square, so that's out. 5 to the 12, lol, that's 5 squared. Well, let's do it the other way around. That could be 5 to the 6 squared, or that could be 5 to the, or that could be 5 to the 4 cubed. So actually this one is squared and cubed, so that's definitely out. And 6 to the 13, well, 13's prime, so I can't do that multiplication trick. And 6 doesn't have any square factors, so yeah, this is not a square or a cube. Okay, Martha draws some pentagons and counts the number of right angles in each of the pentagons. No two of the pentagons have the same number of right angles. Which of the following is the complete list of number? Okay, so pentagons. Here's my pentagon. What's the sum of the angles in it? You should know it's 540 degrees. So, can I have 0 90 degrees? Well, yes, if I just make this a regular pentagon, each of them are 108 degrees, because 540 divided by 8 is 108. So if you want the complete list of possible numbers of right angles, then anything that doesn't... Okay, so A is out and E is out, because we can definitely have a pentagon with 0. Okay, so now the quicker way is to see if 4 is doable. Because if 4 is doable, then B is right by default, so we've saved ourselves a lot of time. And if we had 4 lots of 90 degrees, that's 360. So what would we have to add to 360 to make 540? I think that's 180, isn't it? And that's not an angle, that's just a straight line. So that's not possible. And is it possible with 3? Well, if we've got 3 lots of 90, that's 270. So that means we've got 270 left. So those two angles could be, for example, 135. They might not be the same, but they could be. So it is possible to construct a pentagon with 3 90s and 2 lots of 135s. So in actual fact, 3 90s is possible, so we're going to go for C. Why did I ring it highlighted C? Okay, 8. The picture shows the same dice in different positions, and the dice is rolled. What's the probability of rolling a yes? Okay, so I'm going to draw a net. Yes, I'm going to draw a net of a cube. Here it is. There's a terrible net. There it is. Okay, so let's deal with this first. So if I say that this yes goes in the middle, so that's orientated like this, yes, then if I look up from the E, there is a no up here. So that no, I'm just highlighting this to illustrate what I'm talking about. Essentially, you won't have colouring pencils, but I'm just doing this for show. So yes here. Well, where does that yes go? Well, I trace the O over. So that O is going to wrap around to this side. And then that's going to be an upside down yes. So then that yes is orientated like this. Is that right? Yeah, seems to be legit. Okay, next up. Well, we've got 2 yeses here. Well, one yes. The S reads on to an upside down, and the S kind of points to an E, and it's upside down. So, ooh, that could be, I mean, it might not be, but it could be that this was our green yes, and this was our purple yes. And if that's the case, below the E is a maybe, and it's kind of slanting downwards. So that would mean this is the maybe slanting downward here. So I'll give that a different colour. Let's call that, no, I've had red already, let's have yellow. Okay, so our net could be looking like this. Now let's have a look at the final one. Okay, so according to this, if I look down from the E, there's a no. Well, it can't be the green one, because down from the E is the maybe, so it can't be that. Could it be the yellow one? Well, in that case, down from the E would... okay, so where would that go? That would wrap to here, wouldn't it? So then that E would wrap to there, and look at it up, there'd be a no like that. But then, if I look carefully, the Y wrapping over to the next side, which would be here to here, that would be a no. So in actual fact, that can't be the same yes as the purple one. So this must be a brand new yes. Ooh, and at this point we can stop, because, well, think about it. Well, there's 3 yeses. There's 3 yeses. There's one no that we've taken into account. There's one maybe, and there's two no's. Well, that's the only thing it could be. 3 yeses, 2 no's, and a maybe. So what is the probability of rolling yes? It's 3 out of 6, which is a half. It has to be that. Oh, different green. God damn. So it has to be a half. Okay, this must be a different yes. And you can finish off the plan if you want to, but I just don't think it's particularly relevant. Okay, in the grid, each small square has a side length of 1. What is the minimum distance from start to finish travelling only along the edges or diagonals of the square? This seems pretty easy because, well, do you agree that going 1 along and then 1 down is longer than if I went diagonally? By Pythagoras, that's just root 2. So I want to maximise the amount of diagonals I do, but also not like overdo them. For example, one optimal quick route could be down, down, and then along twice. Or I could have gone along, down, down, along, or I could have gone along, along, down, down. They're all going to have the same length, and that's going to be 2 lots of 1, which is 2, plus 2 lots of those diagonals, which is 2 root 2. So the answer clearly is C. Okay, 3 inhabitants of the planet Zog, lol, met in a crater and counted each other's ears. Immy, Dimmy, and Timmy, is it? There's 3 people, Immy, Dimmy, and Timmy. So from Immy's perspective, she's seeing Dimmy and Timmy. She can see 8 years. So Dimmy and Timmy have 8 years. From Dimmy's perspective, she's seeing Immy and Timmy, and she, is it a she? He, she, whatever, 7. And Timmy, who can see Dimmy and Immy, says that they can see exactly 5. None of them can see their own ears. How many ears does Timmy have? Okay, well, this is a system of equations. You can solve this however you like. Personally, I want to find t, so if I add these two together, I get d plus I plus 2t equals 8 plus 7, which is 15. I know what d plus I is, that's 5, so this is a 5. So 2t plus 5 is 15, so 2t equals 10, t equals 5. That's a really easy one. Okay, the square FGHI has area 80. Interesting, so it's root 80 along, and root 80 is root 16 times 5, which is 4 root 5. Okay. Points J, K, L, M, N, M are marked on the sides of the square, so F to K, G to L. Okay, so yeah, they're all the same. And F to K is 3 lots of... Okay, so this means that this is 3/4 of the length and this is 1/4 of the length. But we know that the whole length is 4 root 5. So actually, what that's told us, if I can move this out of the way. Oops. What that's told us rather quickly is that if that's 3/4 of 4 root 5, then this length here is 3 root 5, and this is root 5, and this is 3 root 5. And then what does it want to do? What is the area of shaded region? Well, what's this length here? Well, we can do Pythagoras on that. Root 5 squared is 5, plus 3 root 5 squared is 9 times 5, which is 45. So it's the square root of 5 plus 45 is the square root of 50. And then when I do root 50 times root 50, the whole thing is 50, but on half of that's the answer is 25. And the answer's there, D. Lovely jubbly. Okay. The product of the ages of a father and his son is 2015. What is the difference between their ages? Oh, another 2015 question. Okay, fine. Well, we know this. 2015 is 5 times 13 times... Oh, God, what was it? 31, was it? Okay. Well, 5 times 403. 13 into that. It's 3, 39, 1, 31. Yeah, okay, fine. I stopped doubting myself. Okay, so father and son. Well, if the product of their ages, I mean, it can either be, well, it can't be the 3 individuals, so we have to group them up somehow. So it's either going to be 5 times 13, which is 65, and the other one's 31, or it can be 5 times 31, lol, which is 155, and 13. And what's the other combination? I've done 5 times that, 5 times that. Or, lol, it could be 13 times 31, which is 403 and 5. Well, put it this way. The difference between 403 and 5 is 398. 155 minus 13 is 142. And 65 minus 31 is 34. Now, in the context of this question, I doubt very much that a dad is 403 years old or a dad can be 155 years old, just because, well, they both exceed average lifetimes by quite a long way. I'm not sure what the world record is for the longest life anyone's had. I don't think it's 155. I mean, I'd believe 130, I guess, or 120, but 155. I don't know. So I'm guessing it's 34. That makes most sense to me. Okay. A large set of weighing scales has two identical sets of scales placed on it. Okay. The two of these weights are swapped. Okay. So if they're swapped, the orientation's the same. Okay. Well, let's deal with some stuff here. So first of all, x is bigger than w, z is bigger than y, but also x plus w is less than y plus z. Okay. So, okay, interesting. So, can we make some substitutions here? If w is less than x, then I can replace this with 2w being less than y plus z. Because if I've replaced x with something that's less than w, then I haven't changed that y plus z stuff. And then similarly, if z is less than z, if y is less than z, then I can replace y with another z, so that's 2z, and I'll still make that bigger than 2w. So actually, we can infer that z is definitely bigger than w. Okay. Right. How does that help? Well, okay. I suppose you could spend a lot of time on this. I mean, I've spent 19 minutes already, but halfway through the paper. Okay, can we do something that makes sense? Right, so if they haven't swapped, what if they, okay, fine. So what is the default thing? So the default thing is this is where w is, this is where x is, this is where y is, and this is where z is. Okay. So let's think about this. If, let's say that, well, let's try the first one, w and z. What does that mean? So if z is here and w is here, that probably would make the scale go to the left because z seems to be very heavy and x was the heavier of w and x. So you've essentially got the two heaviest things. You've got the two heaviest things from each of the individual larger scales. So that's probably going to be a net thing there. Z is probably heavier than x. Y is, well, w looks like to be the lightest thing there. So that could be a potential one. Let's see about w and y. So that could be a potential. What about w? See, this is what I mean. I have not got a counting strategy for this, so I'm just going to go through all of them. What about w and y? Well, if they swapped, this would be where y is, this is where x is. W's over here, and this is z. Well, lol, there's no way z is lighter than w, because we've already proved that, so that's definitely out. That's lols. That's fine. W and x. Well, that's just a nonsense. Because if you swap w and x, then these would just switch, but the right-hand side would be heavier, so that's silly. X and z. Ooh, so this is w, this is z. this is y, and this is x. Well, that's just dumb, because z is definitely heavier than w, so that's just silly. And x and y. Actually, we didn't spend too much time on this, isn't too bad. X and y, so they swap. So this becomes w and y, and this becomes x and z. Ooh, could w be heavier than y? Yeah, it could be. Is x heavier than z? Okay. Could that be a thing? Why could that not be a thing? Well, that may well be the case. W may be heavier than Y, and X may be heavier than Z, but you've got the two heaviest elements of the original thing being lighter than the two lighter. No, that's just silly. Yeah, it has to be W and Z. Okay, the two roots of the quadratic equation x squared minus 85x plus c equals 0. Both prime numbers. What's the sum of the digits of c? Oh, man. Okay, fine. So we've got to think of... Okay. Right, so essentially we've got to find two prime numbers. So two primes that add up to 85. Okay, so 85 is an odd number. So the only way you're going to get that is an even number plus an odd number. You can't have an even plus an even, because that doesn't make sense. And you can't have an odd plus an odd, because that would make an even. So what's the only even prime number? It's 2, so the other one must be 83. So when you times them together, 2 times 83 is 166. So that must mean C is 166. Add them together, 6 plus 6 plus 1 is 13. Boosh. Yeah, it looked harder than it was. How many three-digit numbers are there in which any two differ by 3? God damn. Okay, systematic counting time. Can we use combinations for this? Probably can. Well, I'm doing really well for time, so I'm just going to leave it there. Okay, three-digit numbers. Well, it can't start with 0. Oh, jeez. Okay, it can't. So let's have the first digit, second digit, third digit. Okay, I can't start with 0 because it's not a three-digit number, so I can have any of the numbers 3, 4, 5, 6, 7, 8, 9. Now, if it differs by 3, the only choice after I've picked 1 is 4. For 2, it has to be a 5. But for 3, it can either be a 0, because I can go down 3, or up 3, which is a 6. And for 4, I can either go up, I can go down 3 for a 1, or up 3 for a 7. And for 5, I can go down 3 for a 2, or up 3 for an 8. For 6, I can go down 3 for a 3 and up 3 for a 9. For 8, I have to go down 3 for a 5, and for 9, I have to go down 3 for a 6. So really, I've got branching pathways already, but that's okay. This seems fairly small and countable. And then for the first one, if I'm at 4, I can either go up. Well, let's stick with the thing. I can go down for a 1, or I can go up for a 3. For 5, I can go down to a 2 or up for an 8. For a 0, I can't go down because I'm in the negative, so that's go up for a 3. And for a 6, I can either go down for a 3 or up to a 9. For 1, I have to go up for a 3, so that's 4. For 7, I can either go down 3 for a 4, up. I can't go up 3. So that's that, I think, yeah. For 2, I have to go up 3, so that's a 5. For 8, I can go down 3 for a 5, but I can't go up 3. For 3, I can go down 3 for a 0, or up 3 for a 6. And for 9, I can go down 3 for a 6 as well. I can't go up 3. For 5, I can go down 3 for a 2, or up 3 to an 8. And 6, I can go down 3 or up 3 for a 9. So I have got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Is that all I've got? I feel like there should be more. Let's double check. I mean, that seems right. I missed one. Okay, 1 has to go up 3 to 4, yeah. And 4 can either go down 3 to 1 or up 3 to 7, yes. 2 has to go up 3 to 5, because 2, yep. And 5 down 3 to 2, up 3 to 8, yes. 3 can either go down 3 to 0. I feel like I haven't used this 0 as much. Okay, 0 has to go up 3, or 6 can go down 3 or up 3. Yes. 4 goes down 3 to 1, and 1 has to go up 3. 7 has to go down 3. Is that right? Yeah, 5. Yeah. Yeah. Oh, you absolute spoon. Good one. Good counting. 1, 2, 3, 4, 5, 6, 8. Oh man, I'm such a spong. Such a spong. Oh wow. Okay, good organised counting. So 7, I can either go down 3 to a 4, up 3, I can't do. And 4, I can either go down 3 for a 1 or up 3 to a 7. So then that 18 plus 2. Oh wow, I'm such a spong. Okay, fine. 5 goes down 2, up, yeah, 6 goes down, yeah, so, Okay, I think I've got everything now. Oh man, what a wally. Yeah, so actually, yeah, I think like, I looked at this and thought like, I can get 18. Could I get 20? Maybe. I just feel like when you get towards the upper end of the ones, you might as well just double check and see if you can squeeze out any more. I mean, if I was struggling to get more than 12, I'd probably leave it, but no. So my answer is going to be E is 20. Have I definitely picked all of them? I feel like I have now. Can't believe 7 was missing. I'm such a wombat. Right. How am I doing for time? Oh yeah, easy, 30 minutes. Right, the figure shows 7 regions enclosed by 3 circles. We call 2 regions neighbouring if their boundaries have more than one common point. Okay. Does that mean so this and this aren't neighbouring because they only have one common point of intersection? Whereas this and this are because they've got 1, 2 points. I'm guessing what that means. I mean, that's quite poorly written, but okay. Okay. In each region, a number is written. The number in any region is equal to the sum of the numbers in its neighbouring region. Okay, 2 of the numbers are shown. Okay, fine. So, okay. So this region is when you add this, this, and this up, because yeah, they all have those 2. That's for 1. This is for 2, and then the bottom one has this one and this one. Okay. So 1 plus 2 plus what is question mark? Well, that must be question mark minus 3. Okay. Right. So what must go here? Well, this one shares a border with the 1, and it shares 2 points with this. Okay, so 1 plus question mark minus 3 is question mark minus 2. The bottom right one is only going to share it with question mark and 2, so I believe that's question mark minus 1. And then the top one is only going to share it with 1 and 2, which is 3. Okay. Right. Okay, so let's work backwards then. So 2. That shares it with 3. It shares 2 of its things with question mark, and it shares 2 of its things with this one. So I can now work out that 2 equals 3 plus question mark minus 1. Plus question mark, is it? That's interesting, because 3 minus 1 is 2, so 2 plus the question mark equals 2. I can minus 2 from both sides, so 2 question mark. So question mark equals 0. That's interesting. Does that actually make sense? Let's have a look at it. So if question mark is 0, then that becomes minus 2, that becomes minus 3, that becomes minus 1, that's still a 3, that's a 0. For the middle, 1 plus 2 plus minus 3 is 0, check. For the minus 2 in the bottom left, 1 plus minus 3 is minus 2, check. For the minus 3 there, minus 2, yeah, wow, okay, interesting. Bit weird. But the question mark appears to be a 0. Okay. Petra has 3 different dictionaries and 2 different novels on a shelf. How many ways are there to arrange the books if she wants to keep the dictionaries? Okay, saving time. So she can either have the 3 dictionaries there and the 2 novels there, or she can have the 2 novels to the left and the 3 dictionaries to the right, like that, okay? The order doesn't matter. Well, this is just going to be 3 times 2 times 1, and then this is going to be times 2. So 3 times 2 times 1 is 6, times 2 is 12, so there's 12 ways that way, by symmetry 12 ways that way, so that means there's going to be 24. Okay, how many 2-digit numbers can be written as the sum of exactly 6 different powers of 2, including 2 to the 0? Right, okay, powers of 2. So, okay, so, whoops. So let's write them out. 2 to the 0 is 1, 2 to the 1 is 1, 2 squared is... Oh, Jesus, 2 to the 1 is 2, you silly boy. 2 squared is 4, 2 cubed is 8, 2 to the 4 is 16, 2 to the 5 is 32, 2 to the 6 is 64, and 2 to the 7 is 120. Stop. We've gone into the 3-digit powers, so we stop there. Okay, how many are there? There's 1, 2, 3, 4, 5, 6, 7. Oh, and we only need 6 different ones. So out of these, how many ways are there of making... Okay, so we've got to get rid of one. Okay, so first guess is if we eliminate the 2 to the 6, that would be fine. Because if I wanted the sum of 2 to the n, that's the same as 2 to the n minus 1, isn't it? I.e. 1 plus 2 is 3. And that is the sum up to 2 to the 1. And that's the same as 2 squared minus 1. I.e. the sum of 1, 2 and 4 is the same as 8 minus 1, which is 7. The sum of 1, 2, 4 and 8 is 15. And so on. So if I get rid of 64, then the sum of these 6 should be 63. Okay, so it's definitely 1. So that 0 is done. Could I eliminate the 32 in this case? Well, 1 up to 16 is 31. 31 plus 64 is 95. So yes, I could do that. So that's totally fine. So I can get more than 1. So that's done. Could I eliminate the 2 to the 16? So 32 plus 64 is 96. Lol, that's going to be... Yeah, so even if I add the 4, it's going to be 100. And then if I eliminate smaller ones, I'm just going to be making it bigger. So it looks like I can only have 2. Okay, 20. In the triangle FGH, we can draw a parallel to its base. The areas of the shaded region are the same. The ratio HX to XF is 4 to 1. Okay, so this is 4/5 of the total thing. This is 1/5. So that means by similarity, this is 4/5 of the perpendicular height. So this white triangle is 4/5 scale factor, so that's going to be 16/25 of the area of the triangle by similarity. Why are they similar triangles? Because this angle is the same as this one, this angle is the same as this one, and they all share this angle the same. So by similar triangles, that's because, yeah, it's going to work. So this grey thing is actually 9 out of 25 of the big triangle. So if this thing is 9 out of 25, then we've actually got 3/5 of the height there and 3/5 of the height there, which means this is 2/5. So this is really not drawn to scale at all. So what am I looking for? HY to YF. Oh, I've got that. It's 3 to 2. So the answer is 3 to 2. Bosh. In a right-angled triangle, the angle bisector of an acute angle divides the opposite side into side elements of 1 and 2. Oh dear. Right, okay, so let's add a page. I feel like I'm going to have to doodle. So what's this saying? Right-angled triangle. Right-angled triangle. And I've created an angle bisector. Something like that, where this line side length's 1, this is 2, that's 90, this is some alpha as well. Okay, what are we trying to find? What is the length of the bisector? Okay, so what we want, ideally, is this length here. Okay, I feel like there's some Pythagoras going on here. So a couple of things. This angle here, trig, do we? Okay, fine. So what we can do is draw a line from here to here, where that meets 90. And immediately, by similar triangles, I can spot that this length is 1 here. This is 90 like that. And this angle here is 90 minus 2 alpha. And this angle here must be 2 alpha. Is that right? No, wait. Yes. This angle must be 90 minus alpha. This angle must be 90 minus alpha. Okay. So, a couple of things. By looking at this triangle up here, it's got a hypotenuse of 2 and a base of 1. So, that means this length is root 3. And then, by similar triangles, if we call this length x, then this base is also x. And then we've got this massive right-angled triangle here, such that 1 plus 2 is 3 squared, plus the base squared, which is x squared, equals the hypotenuse squared, which is x plus root 3, all squared. So it's going to be 9 plus x squared, and if you expand this out, this is going to be x squared plus 2 root 3x plus 3. Can minus the x squareds both sides, that's great. Minus 3 from both sides, that's 6 equals 2 root 3x. Divide by 2, 3 equals root 3x. Divide by root 3, so x equals root 3. Okay, that's not solved it though, because we wanted that green bit. So now if we consider that we've got a root 3 base there, a 1 there, and we want the hypotenuse, so 1 squared plus root 3 squared, which is 3, equals h squared. 1 squared plus 3 is 4. If h squared equals 4, h is clearly 2. I've got them as roots. Okay, well 2 is just root 4. That was fairly straightforward. Okay, we use notation AB for the 2 digits with digits AB. Let A, B, C be different. How many different ways can you choose? Oh dear. Right, okay. So, because A, B and C are all the tens digits, that clearly means that A is less than B is less than C. I don't think that was given to us in the question, but that's useful. Okay. Fine. Right. How many ways can you choose A, B, and C such that? I don't think we need to know the second digit so much, do we? Because I could pick the largest value in the tens, and I know that's going to be less than even the smallest in the next tens up. It doesn't particularly matter. It doesn't matter if I change this 9 to a 7 or a 3 or a 2, or I change this 0 to anything else. The fact that 20s are bigger than 10s is the main takeaway here. How can I deal with this? Well, also, it looks like A, B and C have to be greater than 0, so it's numbers from 1 to 9. Why is that? Because these are 2-digit numbers. You don't say, well, 09, we just write 9. So they have to be numbers from 1 to 9. Okay. Right, so let's think about what's going on. So A, let's think of combinations for A, B and C. If A was 1, 2, 3, 4, 5, 6, 7. Okay, so we can have 9 combinations for this. And then for B, we could have any 8 combinations, then 7, then 6, then 5, then 4, then 3, then 2, then... Or if there's only one combination, that eliminates it for C, right? So that should be a 6, that should be a 7. So really, A can only be from 1 to 7. Because if A was 8, B would have to be 9, and then C doesn't exist. Fine. And then, well, then C depends there as well, doesn't it? Okay. Is there a quicker way of doing this? Well, let's look at the B's then. B has to be at least 2. So if B is 2, C can be from 3 to 9, 3, 4, 5, 6, 7, 8, 9, so that can be 7 things. If B was 3, C can be 6 things. So this is the B number, and this is the combinations. Okay, so if B was 4, there's only 5 things it can be. 5, 6, 7, 8, 9, yeah. And then if it's 5, it can be 4 things. 6, it can be 3 things. 7, it can be 2. 8, it can only be 1 thing. Okay, so let's look at the numbers. So when A is 1, then there's 8 possible choices. So we have to add all these numbers up. And 1 to 7 is n times by n plus 1 over 2. So that's going to be 7 times 7 plus 1 over 2, which is 28. So actually, so there's B can be 8 things. Have I got that? 1, 2, 3, 4, 5, 6, 7. B can't be 8 things. B can only be 2 up to 8. 2, 3, 4, 5, 6, 7, 8. It can be 7 things. So this has to be 6 things. This has to be 5, 4, 3, 2, 1. Yeah. 5, 4, 3, 2, 1 thing. And then down here, C has to be 1 thing. Right. So there's 7 times 7 plus 1, so that's 56. Well, 8 over 2 is 4, 7 times 4. So there's 28 combinations there. When it's 6, so what did I say? There's 28. If I minus 6 from that, now 22. Is it? So there's 22 there. No, we're a minus 7, you silly boys. 21 there. 21, minus 6, 15, minus 5, 10, minus 4, 6, minus 3, 3, minus 2. Yeah, okay. So actually, we've got to sum these up. Is that right? Okay, so 8 plus 1 is 9, plus 5 is 14, 20, 24. And then 1, 2 is 2, 40, 60 plus the 2, 84. Yeah, okay. Maybe there was a quicker way of doing that, but 84, okay, there you go, bosh. Okay, when one number was removed from the set of positive integers from 1 to n inclusive, the mean of the remaining numbers is 4.75. What no? Oh, geez, okay. Right, so what is the, okay, the mean is the sum of n divided by the amount there are. So the sum of n is n times by n plus 1 over 2. So the mean is going to, so, okay, what's the largest value this new mean could be? Well, the largest is if I took away just 1, right? So if I did n times n plus 1, the total, and then I minused 1, and then divided by the amount of things there are, n minus 1. So this is the largest. It's the largest it could be. Minus 1 is 2 over 2. So this is going to be n times n plus 1 minus 2 all over 2 lots of n minus 1. If you expand the top, you're going to get n squared there. Going to n times, that's going to be plus n, and you've got a minus 2. And this is going to be 2 lots of n minus 1. I want this to cancel down. I spot that this factorizes to n plus 2 times n minus 1. So this is going to be n plus 2 times n minus 1 all over 2 lots of n minus 1. That cancels. So we've actually got the largest the mean could be is n plus 2 over 2. Now what's the smallest it could be? Well, that's if we took away the biggest number, so it's going to be n plus 1 over 2 minus the largest number, which is n, so that's 2n over 2, and then I divide it by n minus 1 because I want to find the mean. So n times n is n squared, n times 1 is an n, but then I'm minusing 2n, so it's going to be n squared minus n over 2 lots of n minus 1. N squared minus n is just n times n minus 1. This is going to be over 2 lots of n minus 1, so that and that cancel. So this is going to be n over 2. Right, now the mean was 4.75, wasn't it? So, okay. So, if the smallest the mean is that, then doesn't that mean n over 2 is bigger? No. That 4.75 might not be the smallest, so that could be greater than n over 2. No. Yes. So that means n is less than 9.5. Okay, and then the largest it could be is that, which means n plus 2 over 2. If it is the large, well, it could be less than or equal to. Well, it can't be equal to 9.5 because n has to be a whole number, so it's clearly less than 9.5. That's silly. But then if n plus 2 over 2 is 4.75, and I times by 2, that's 9.5. Then I minus 2, so n is greater than or equal to 7.5. So clearly it has to be bigger than 7.5 because n is an integer. So really, actually, that's quite nice because then that's eliminated n to 8 and 9. Okay. What other things could we do? Right, 4.75. Okay. Right, if we're dividing by n minus 1, it's got to give 4.75. 4.75, I want to say, is 19 over 4. So n minus 1 has to be 4 or a multiple of 4. I mean, if we divide it by 3, there's no way I can divide something by 3. I can't divide integers by 3 and get something over 4. So what is n minus 1 in both these cases? Well, if it's 8, that goes to 7. And if it's 9, it goes to 8. Well, it's clearly this. I can't divide by 7 and get quarters. So n has to, aha, n is 9. Aha. Right, so what's the sum of the numbers from 1 to 9? It's going to be 9 times by 9 plus 1, which is 10 over 2, 90 over 2, so it's 45. And the total, so the mean was 19 over 4. And if I times that by 8 numbers, because, you know, if I had 9 numbers and I took one away, that means there's 8 numbers. So 8, that's 2, that's a 1, 19, that's 38. So how do I get from 38 to 45? It's 7. Yeah. 7's the answer. Okay, 10 different numbers, not necessarily integers, are written down. Any number that is equal to the product of the other 9 numbers is then underlined. At most, how many numbers can be underlined? Okay, right, so we've got 10 digits. What is this? That's question 24. Okay, 24. So we've got 10 digits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, there can't be a 0 because then if I chose something else, then all of these others would be times by 0, so that would have to mean this is 0 and they all have to be different. So they cannot be 0. That's not the easy fix. Let's pick another one. Let's pick 1 and minus 1. So if I was to choose minus 1, then I just have to have 1 times by a bunch of stuff where one of them's negative or another 2 or another 4 are negative. And they all have to be reciprocals. Let's say alpha, 1 over alpha, beta, 1 over beta, gamma, 1 over gamma, delta, 1 over delta. Because if I multiply all these things together, they're all going to equal to 1, and that negative in front of the alpha is going to work out. Okay, so 1 can definitely be squared. If I choose the 1 there, then the minus and minus from the first two will be positive, and I know the others are reciprocal, so that will be fine. Is it possible to square a third one? Okay, so that means minus alpha equals 1 times minus 1, which is minus. That's a good start. And then I've got these times to 1, these times to 1, these times to 1, so I've actually got minus 1 over alpha. Interesting. So if I times by alpha both sides, it's going to be minus alpha squared equals minus 1. But then alpha squared is going to equal 1, which means alpha is plus or minus 1, and we've already got those already. Okay. And then by similar argument, I could have done it for that, and that would have been the same as well. Because, yeah, if I'd have had 1 over alpha, that must equal, well, the rest times to 1. So really it's these three. So then that's going to equal to alpha, and then I'm going to have the same argument there. 2. Yeah, I think it's just 2. I think that just have to be 2. Is there any way of doing it with like squares and stuff? No, I don't think so, because then you could say like alpha could equal some r squared or to the power of something. And then you'd have a similar argument, and okay, there's no squared numbers or surds or anything like that. Yeah, you couldn't have anything like a plus root b. But then 1 over a plus root b would be a minus root b. And then when you times them together, you're going to get a squared minus b. And then that's no, I don't think so. I think that's going to lead to too many things. I'm guessing. I'm pretty sure you can only circle 2. That would be my gut instinct if I was to put this down. Okay, 7 minutes left, Jesus. Okay, several different points are marked on a line, and all possible line segments are constructed between the pairs of points. One of these points lies on exactly 80 of these segments. Okay, right. Okay. Did it say 7 or several? Several, goddamn. Okay, fine. Okay, so here's my line segment. And let's say I start at the end point A. Doesn't matter about the spacing, I don't think. That's C, D, and so on and so on and so on. And then there's a last point there called gamma. Right, okay. Actually, this is annoying me. I think I'll move this so it's here. Okay, cool. Right, so one of these points lies on exactly 8. Okay, all possible line segments are constructed between pairs of points. Okay, so does that mean I can consider AB, and I could consider BC, and I could consider A to C, and I could consider B to D? Okay, fine. One of these points lies on exactly 80 of these segments, not including any segments which then... so they can't be an endpoint. So A to B includes no points, but A to C includes just the point. Okay, right. Okay, any of these points are... Okay, fine. So let's look at A. Well, A is not going to have any segments that's going to be part of, and same as the end one, just by symmetry, because they need a point over here. That's not going to work. Okay, so let's have a look at B. Well, that has to be from A to any other point. And if there's n of these things, then n minus 1. So really, there's n minus 2 connections, because it's A to any of the n minus 2 connections this side. So B, there's just going to be n minus 2 connections. Okay, fine. Let's develop a pattern to see what's going on. C. Well, it has to be A to any of the D's and beyond. So that's going to be an n minus 3 plus, and then B's to any of the D's. That's another n minus 3. Ooh, so we've actually got 2 lots of n minus... Ooh, that's interesting. We've got 1 lots of n minus 2. So then would that be 0 lots of n minus 1, which is... Ooh. So is it in the form k lots of n minus... no, hold on. Be careful. If this is k equals 0, the 0th one. Okay, fine. So that would be k plus 1. Okay. Right, so then does that mean this one is 3 lots of n minus 4? Well, it seems to be the case because you've got this point here, the next one along, there'd be n minus 1, n minus 2, n minus 3. So you've got n minus 4 to the right of it, and you've got 1 lots of n minus 4 of all the a's to that, and then you've got the b's, and then you've got the c's. Yeah, so yeah, okay, cool. Okay, k has to be an integer. K has to be a positive integer. Interesting. So if it lies on exactly 80 of these points, then k lots of n minus k plus 1 equals 80. So n minus k plus 1 equals 80 over k, and this has to be an integer. Okay. Okay. Fine. So what are all the factors of 80? Well, it's not too bad, I don't think. So 180, 240, 3 no, 4, 10, 5, 8, 6 no, 7. Okay, so we've got 5 times 8 is 80. Steady on. 516. The 6 doesn't go. Oh, 4 times 10. Are you mental? You actually mental. Jeez, what is my life? 6, 7, no. 8 is, that's 10. No. Okay, fine, we've got it now. Okay, so let's sub some things in. So, n minus, well, it's clearly not going to be these ones. That's dumb. Because 80 divided by 1 is 80. Well, okay, let's do a thing. If k is 1, what is n minus k plus 1? And what is 80 over k? So if k is 1, we've got 80 over 1, which is 80, and then you've got n minus 1 plus 1, which is 2. Lol. Okay, I mean that could be. So n would be 82, but then we can do a similar thing for 90, can't we? So then 90. 1, 90, 2, 45, 3, 30, 4, doesn't go, 5, 18, 6, goes 15, 7, no, 8, no, 9, 10. Okay, so 90 over k. Well, if we did 90 over 90, which is 1, n... sorry, hold on. Yeah. Okay, so for that, okay, so we're trying to solve simultaneously 90 over, say, a different k equals n minus k plus 1, and we're trying to solve 80, let's say it's k1, that's k1, and this is k2, n minus k2 plus 1. I feel like it's going to be in the middle, because if it was towards the end, I don't think that makes sense. Okay, so 90 over... Okay, so if k1 is 6... are there any that are the same? What about these? Okay, so the 5s are the same, so let's try 5 and 6. So when 90 is over 6, that's going to give 15. Does that equal n minus... the k was 6, 6 plus 1 is 7, n is 22, and then when k2 is 5, I've got 80 over 5, which is 16. That equals n minus k2, which is 5 plus 1, which is 6. N is 22. Yeah, boy. Cool, that's a bit lucky. So yeah, bit of instinct there. That's done. Whew, close. But yeah, yeah, I don't know. I think I just went for it because I'm sure there's a better way of doing this. And in the actual thing, I wouldn't be talking out loud and I'd be working a lot quicker, probably making more mistakes in all fairness. But yeah, interesting question paper. Work through them. I mean, they're great. They really are. yeah.